Good morning, everyone. Good morning, everyone. My name is Shen, and I'm from Hohai University, China. Today, I will present our work titled RadGS-Reg Registering Spine CT with Biplanar X-rays via joint 3D radiative Gaussian reconstruction and 3D to 3D registration. I will introduce this work from the following 4 aspects: background method, experience, and the conclusion. We know that in spinal surgery navigation, 3D pose of the preoperative CT by using intraoperative biplanar 2D X-rays is the critical step. During robot-assisted spinal surgery, CT2 X-ray registration must be highly precise, within 2 millimeters and fast, almost 3 seconds. Our task is to register per-operative CT to intraoperative X-ray. Our task, usually we have 2 views, AP view and LAT view. Nowadays, the dominant 2D, 3D registration methodology is called random compare. That means render the 3D CT volume to DR images and compare the DRs to intraoperative X-rays. By iterations, the pose of the CT volume can be finally derived. However, the main problem of the random compare is time-consuming, caused by DR generation. Actually, if we could reconstruct the precise 3D Gaussians by 2 orthogonal X-rays, then registering per-operative CT to 3D Gaussian would be much more robust and effective in contrast to the traditional random compare methods. Here comes the key problem: how to reconstruct the precise 3D Gaussians by merely biplanar X-rays. That's quite challenging. Why? Because the 3D Gaussian reconstruction is dominant for reconstructing X-ray into 3D volume. The sort-time methods, however, depend on dense view X-rays. To address this challenging issue, we have the following observation. That is, the preoperative CT with ground truth pose is the target of the 3D reconstruction. That means the CT volume provides the exact shape, though we do not know its pose. On the other side, the 3D Gaussian reconstruction can provide the relative exact pose of the 3D shape. However, this shape is worse from just biplanar views. Actually, we found that these 2 processes can complement for each other. So, as analysis above, we propose synergistic training of 3D to 3D registration and 3D reconstruction to handle these 2 tasks together. That means 1 stone, 2 birds. That's our first technical contribution. Our second contribution is to mitigate disturbance of the neighboring vertebrae by using counterfactual attention learning. After extensive experience, our trained model achieved SOTA performance of both 2D, 3D registration as extremely sparse view 3D reconstruction. Next, I will introduce the method part. Let's main workflow. First, let me introduce our synergistic training. At first stage, we trained the RadCam to predict the Gaussian parameters, and this net can provide a volume to RadGam. At second stage, we trained the RadGam net to predict the final pose by learning the relative spatial position of the Gaussian volume and the CT volume. At final stage, we jointly compute the losses and the synergistic train the network parameters for RACM and RAGM. After training, we call the whole framework as RadGS-Reg. At the inference stage, the overall process is to import the biplanar X-rays and preoperative CT into RadGS-Reg, which outputs the final pulse and the intraoperative volume. That's our goal, one stone, two birds. Let me introduce the detail of the RACM network. The input of RACM is biplanar X-rays. Then the image encoder will extract the image features. We use car module to help net to predict precisely volume. Next, let me introduce the rasterizer and the voxelizer in RACM. The rasterizer can project images to compute the loss against the ground truth images, thereby updating the parameters of RACM. The voxelizer can convert Gaussian parameters into a volume. That's our loss function. At first stage, we use MSE loss, SSIM loss, and the total variation loss. At second stage, we use normalized cross-correlation loss, geodesic distance loss, and the SSIM loss. At final stage, RACM and the RAGM are synergistically trained. The loss function is as follows. Thirdly, I will introduce the experience parts. We use simulated and real data sets to train and test our model. The evaluation metrics for volume reconstruction is PSNR and SSIM. The evaluation metrics for registration is MTRE, capture rate, time efficiency, and success rate. The real data set was provided by company of surgical robots. First, we compared with the baseline method of MVS to verify ours. We found that the method achieved the SOTA MVS results. Second, we performed baseline comparison on 3D reconstruction. Our method achieved the SOTA reconstruction results as well. Furthermore, we performed baseline comparison on CT2 X-ray registration. Actually, we achieved the SOTA performance on aspects of MTRE, capture rate, success rate, and runtime. Finally, we have a conclusion. First, we present RadGS-Reg, a unified framework for vertebral CT2 X-ray registration by synergizing 3D reconstruction and 3D to 3D registration. Second, we integrate car module to mitigate the influence of the vertebral overlap interference. Our future work will focus on handling non-rigid deformation and Gaussian segmentation for broader clinical application. Thank you, that's all.